today what we will do is we will look for newer methods for solving second order linear differential equation. Okay. Today we will look for in the last couple of classes we were looking at solving this differential equation, second order linear homogeneous differential equation by separation of variables method. Today we will see a series solution which is called Frobenius method. Okay, it is called Frobenius. Okay, Frobenius method. So let's start without spending much of time on the method. We will directly apply the method and then we will deduce what are the steps involved in this method. Okay. So here, as you know, the equation y double dash plus p of x y dash plus q of x y is equal to 0. This is homogeneous because you have all the terms are having y, y dash and y double dash, either of them. If there were another term, say something like f of x, which does not have either y or its derivatives, then this equation is no longer homogeneous. We know that this is non-homogeneous and this term is many a times called the source term. Okay, so we are not looking at only the homogeneous part. And how it is linear because you have all the power of y, y dash and y double dash are 1. The degree of y, y dash and y double dash are all 1. There is no cross terms, so that this is linear. So in general, we will show actually more precisely that there exist only two solutions for a second order homogeneous linear differential equation. So let's say that if it were y1 of x and y2 of x, then the general solution for this is some constant. It is all linear combinations will work. So c1 y1 plus c2 y2 of x is the general solution for this. So later we will show explicitly that there cannot have a third solution, independent solution for a second order homogeneous linear equation, differential equation. Okay. So today we will now use the Frobenius method for solving. Say let us take the simple harmonic motion equation. Okay, y squared y double dash plus omega squared y is equal to 0. This is the same equation we came across in many times when we solved the Laplace's equation or the Helmholtz equation in cylindrical polar coordinate system and in spherical polar coordinate system, right? Because there were we wrote dy y double dash is equal to minus omega squared y. Fine. So what is the solution? The solution we know already because it is simple harmonic motion. So it is either sin y is equal to sine omega x. So actually the y1 is sine omega x and y2 is cos omega x. So we will, instead of using that way, we will try. This is like using a cannon to catch a fly or kill a fly. Okay, because we don't really need. We know the different methods for solving this, and we already know it. But still, only to find the understand the method, we will try. So what we do is we are trying to find out the second order differential equation, homogeneous differential equation, which is our simple harmonic motion. In this case, we will use um, a series solution. Okay, what we basically use is that, okay, you know what is a series, but a series. Let, first of all, let y of x, the solution. Okay, the solution is, some x raised to k into a0 plus a1 plus a1x, a1x plus a2x square plus etc. in the general term an x raised to n, and it is still going on. Okay, it's then running. We put the equation here itself. Summation over some lambda equal to 0 to infinity. Okay, it runs from 0 to infinity. A lambda x raised to lambda plus k. Explicitly, what we say is that, this series, okay, a0 is not equal to 0. Okay, this here we assume that a0 not equal to 0, because a0, if a0 is 0, the lowest value will be defined by a0, basically a0 x raised to k in k. So k is such that, it starts from the lowest possible value for y of x. So if you say a0, it will move to a1. Okay, so we don't want that. We need this lowest possible representation from a0 x raised to k. So you don't need to worry about why it is, but we can say that, the first assumption is that, we have a series solution for our y of x, and then in that a0 is non-zero. So let's do this. What will be now? Can you say what is dy by dx? We need to find out dy by dx is equal to, I can write it straightforward from this way. Okay, what will happen is that, every term will be, let me write it, it is summation, because summation is still running from lambda equal to 0 to infinity. Instead of a lambda x raised to lambda, it will be lambda plus k into a lambda x raised to lambda plus k minus 1. As simple as that. It is മനസ്സിലാവുന്നില്ലെങ്കിൽ you have to go up and do it yourself, and later you can verify. It is nothing, because if this follows this, then the derivative of this will follow this. Okay, lambda plus k into a lambda x raised to lambda plus k minus 1. And what will be d squared by ds square? We need, because what we are trying to do is we find y dash and y double dash. Okay, and we will substitute back in this equation. That's it. Okay, in this equation, because you don't need dy by dx here, but to find out d squared y by dx square, we need this. That's it. So what is d squared y by dx square is equal to, again, summation lambda equal to 0, lambda plus k into lambda plus k minus 1 into a lambda x raised to lambda plus k minus 2. Now the job is simple, just substitute. Okay, just substitute it in equation 1, both y and y double dash. Okay, so we get, substituting this equation, y and y double dash. Okay, so you have to write it like that. So what is y double dash? Y double dash is this, summation lambda equal to 0, lambda plus k lambda plus k, my mouse lost, lambda plus k minus 1 a lambda x raised to lambda plus k minus 2, this is y double dash, plus omega squared y is again lambda equal to 0 to infinity, yes, since infinity is must because it's an infinite series, a lambda x raised to lambda plus k equal to 0. See, essentially this is two series now, and what we are going to say is that if I have, basically this is an interesting thing, if I have two series, okay, n equal to 0 to I don't need n running from n1 to n2, some a n x raised to n is equal to n running to n1 to n2 bn x raised to n, then it is easy to show that a n for every n is equal to bn. You cannot get different combinations. It is actually pretty simple. If you look into it, you have, if there are n number of indices, okay, n1 to n2, you have that many equations and that many variables only. So it's pretty not that difficult to show, but this is what we will be using in a different context, but it is basically same. Okay, so that's fine. That's after that. Now the first step, okay, we got this equation. You put lambda equal to 0, the first step, okay, put lambda equal to 0, and if you put lambda equal to 0, the lowest order will be lambda is 0, not k, okay, it will be a0 x raised to, and look for the lowest power of x. Here it is lambda plus k, and here it is lambda plus k minus 2, so this is the lower one, and here when you put lambda equal to 0, it will be x raised to k minus 2, and so you equate, put lambda equal to 0 and equate the power of x raised to k minus 2. X raised to k minus 2 is the lowest power in the term once you put lambda equal to 0. Okay. So what you are trying to see is that, I mean, here this you can write, this is a summation is equal to minus omega square another summation, exactly like I told you on the other, in this equation. So you term by term you can equate. So coefficient x raised to k minus 2 should have, the coefficient of x raised to k minus 2 should be equal on either side. And let's look what is that. So what is the coefficient of x raised to k minus 2 when you put lambda equal to 0 here? X raised to k minus 2 is, this will take a little bit of time, so I will go very slowly, okay, but then we can, once you understand it, it is not that complicated. So once you put lambda equal to 0, the coefficient here is x raised to k minus 2, the power is x raised to k minus 2, and the coefficient is simply put lambda equal to 0 in this term. So it is k into k plus k minus 1 a0, k into k minus 1 into a0. And what is the coefficient of k minus 2 here? The first term is 0, a0, first term is a0 x raised to k, there is no term, the next term is lambda equal to 1, so x raised to k plus 1. So the lowest term is here is x raised to k minus k, sorry, there is no k minus 2, x raised to k minus 2 term here. So that the coefficient is basically 0, is equal to, right hand side there is again no coefficient, so it is 0. Or this is not needed, right? So it is giving you that this is equal to 0, straightforward. Now just for, okay, we will do that in a while. And we have already seen that, I mean, we have already took it for granted that A0 is non-zero. So this gives you, okay, this equation is called indicial equation. Indicial equation, which you got by equating the lowest power of lowest index of x by putting lambda equal to, after putting lambda equal to 0. Fine. So it is the indicial equation which you got after, which you got equating the lowest power of x after putting lambda equal to 0. And here indicial equation A0 is non-zero. So you have from the indicial equation either k equal to 0 or k equal to 1. Normally k equal to 0 and k equal to 1. K equal to 0 will give you an equation, k equal to 1 will give you the second solution. Okay. There are certain conditions. We will see why and how this equation works or fails. Okay. So this is the solution, k equal to 0. Now the second step. Okay. Let's put lambda equal to 1 and repeat the same and equate the power and equate the power of, not power, sorry, this is not power, it's coefficient, right? Coefficient of the, coefficient of x raised to, which will be the lowest one, anybody? Lowest power, once you put lambda equal to 1, this is 1 plus k, this is k, a1, x raised to k1, k plus 1 minus 2, here it will be k plus 1 only, so this is again this one. So x raised to 1 plus k minus 2 will be x raised to k minus 1. Nothing, you have x raised to k minus 2 here, the next higher term will be x raised to k minus 1 when you put lambda equal to 1. There is no complicated stuff. And it is going to be a little tricky. You in the same equation, now you need to have lambda equal to 1 and you have to look for the power of x raised to k minus 1. Here also lambda is 1, so lambda is equal to 1 means first term itself is the power, okay, because then this is x raised to k minus 1. So it is k plus 1 into k a1 x raised to k minus 1. So that is the coefficient. And similarly here omega square a lambda, the first term when you put lambda equal to 1 is a1 x raised to k plus 1. There is no k minus 1 term. There is no k term. There is no k minus 1 term. So this is going to be 0. Here You actually say the other way, A1 now put or set A1 is equal to 0. In this case is actually interesting. You have an equation k equal to, in this case we have already found that k can be, from the lambda equal to 0 equation, k can be 0 or k can be 1. When you put k equal to 0, this equation is 0, you don't need to have any value of a1 is possible. But when you put k equal to 1, this is k is 1, k plus 1 is 2, 1 into 2, a1 is equal to 0. There is no way this can be 0 and a1 has to be 0. Here you can deduce it, a1 is equal to 0, but in general we don't need to do that. We can say no, a1 is 0. That is the method of part of the solving this equation. Okay. Now in the beginning we set everything equal. Now at the end some power, okay, they become equal, so that the series terminates after a particular power. So let's assume that the series terminate for a particular power, say x raised to the third step is put let the series terminate after x raised to some particular one, k plus j, some value j, meaning the coefficient of x raised to k plus j is 0. Okay. So what is the coefficient of x raised to k plus j and the higher order terms? Okay, because it stops from the, so that all powers, all coefficients higher than the power k plus j are 0. So what is the if I now equate the coefficient of, this is a little bit tricky, this is, if you understand this, the entire solution is not to you now. Okay, the method is learned, so pay attention. What is the power of x raised to k plus j in this equation? Okay, or in this term, the first, what is the coefficient of x raised to k plus j here? Here it is easy, all you have to do is put lambda equal to j. When you put lambda equal to j, the power x is x raised to k plus j. So what is the coefficient? Coefficient is omega square a j instead of lambda. Here this is going to be a little bit tricky. You need x is equal to x to the power of k plus j, or lambda minus 2 is equal to j. Okay, lambda plus k minus 2, x raised to lambda plus k minus 2, we need to put k plus j. So you can cancel the k's, or lambda is equal to j plus 2. If you put lambda equal to j plus 2 in this equation, you will get the, in this coefficient will be that of x raised to lambda, x raised to k plus j. So what is that? Put lambda is equal to j plus 2. So this will be, let me write it. So it will be, the first term will be lambda plus 2 k plus k and 1 minus. So I can say this as k plus j plus 2 into k plus j plus 1 because 1 minus. A lambda is j plus 2. A j plus 2. Lambda is j plus 2. So it will be k plus j plus 2. Lambda is j plus 2. So this is minus 1. So it will be k plus j plus 1. J plus 2 minus 1 is j plus 1. A j plus 2. X raised to j plus 2 plus k minus 2, which will be x raised to j plus k. So that is what we need. The coefficient of x raised to k plus j is this, plus there is the second term. Omega square. As usual, here there is now, if you put lambda equal to j, it will be the power will be matching x raised to k plus j. So the coefficient will be omega square aj. Omega square aj equal to 0. This is an interesting equation, okay? What is interesting? Aj is there is a recurrence relation. If you know aj, you can calculate aj plus 2th term. And it will ensure that after x raised to k plus j, this term will vanish. I mean, these two equations will vanish. So let's write aj plus 2 aj plus 2 is equal to minus omega squared aj divided by k plus j plus 2 into k plus j plus 1, right? This you can call equation 3. See, in the whole point we want to have is a1 is equal to 0 and a0 is non-zero. Then you have two situations, k equal to 0 or k equal to 1. Now all you have to say is that what happens to k equal to 0 here in this equation and k equal to 1 in this equation. Okay. First of all, we can say that no matter what you do, we have assumed a1 equal to 0. So if you put j equal to 1 in this equation, a1 is 0. So a3 is 0. If you put it back a3 j equal to 3, it tells you that j plus 2 is the term is 0. A3 is 0 implies a5. So meaning a1 equal to 0 implies a3 equal to 0, which implies a5 equal to 0 and goes like this, which means all our a1 equal to a3 equal to a5 equal to etc. are identically 0. ഈ ഇക്വേഷൻ മനസ്സിലാവാത്തവരുണ്ടോ? സി നമ്മൾ j equal to plus lambda is equal to j plus 2 ഈ ഒരു ഇക്വേഷനിൽ മാത്രമേ കൊടുക്കുള്ളൂ. നമുക്ക് വേണ്ടത് എന്താ? x raised to j plus k ടേം വേണം. അപ്പോൾ ഇതിനകത്ത് x raised to j, ഈ രണ്ടാമത്തെ ടേമിനകത്ത് x raised to j plus k വേണമെന്നുണ്ടെങ്കിൽ lambda j കൊടുത്താൽ മതി. അപ്പോൾ you will put lambda equal to j in this case and lambda equal to j plus 2 in this case. മനസ്സിലായോ? കാരണം ഇവിടെ ലാംഡ ഈക്വൽ ടു ജെ കൊടുത്തു കഴിഞ്ഞാൽ എക്സ് റേസ് ടു ജെ പ്ലസ് കെ മൈനസ് 2 ടേം ആണ് കിട്ടുക. നമുക്ക് ജെ ഏത് വേണമെങ്കിലും എടുക്കാമല്ലോ. ഇവിടെ ലാംഡ ഈക്വൽ ടു 0 മുതൽ ഇൻഫിനിറ്റി വരെ ഉണ്ട്. യു കനോട്ട് റൺ ലാംഡ മൈനസ്, ദാറ്റ്സ് ഓൾ. ക്ലിയർ അല്ലേ? ഓക്കെ. സോ നൗ ദിസ് ഈസ്, ഐ മീൻ, the crucial part, that equation 2. you get a recurrence relation. Why recurrence? Because if you get the jth term, we just rearrange this. Okay, if you go to aj plus 2 will be minus omega squared aj divided by k plus j plus 2 into k plus j plus 1, and this is simple rearrangement. Now we have already said a1 we are going to take as 0. So when a1 is 0, you get j equal to 1. Put j equal to 1 in this equation. When you put j equal to 1, this is j equal to 1, so a3 is equal to something into omega squared by this will come, we will look into it later, omega square by k something, but multiplied by a1 is 0. So this tells you that a1 equal to 0 implies a3 equal to 0. a3 equal to 0, if you substitute in this equation, it means a5 is equal to 0. So continue like that, you know all odd coefficients are zeros. Okay. Now we have said a0 is not 0. So you cannot do this. There will be coefficients a0, a1, a2, a3, a4, etc. Right? All even powers. So let's look for two cases now. Case 1, I will add, remember this equation, okay? I will use this equation. This equation, Control C. Okay, this equation is our equation number 3. We will put the case 1. Case 1, k equal to 0, which is from the initial equation. Okay, k is equal to 0, and in where a0 is not equal to 0. a0 is not equal to 0. Now when you put k equal to 0, this equation becomes aj plus 2 this will become aj plus 2 is equal to minus omega squared aj divided by k is 0 here, so it is j plus 2 into j plus 1. Clear a line? Nothing, you put k equal to 0 here. So you get the recurrence relation for the case k equal to 0. Now we know that a0 is not equal to 0. So let's see what is a2. a2 from this equation, put j equal to 0, then we get, no, I will not take the mouse, okay. Put j equal to 0, then we get a2 is equal to minus omega squared a0 divided by 1 into 2. J equal to 0 means this is 1 and this is 2, which I can write in fact here straightforward because I know it will be useful for you later. Minus omega squared a0 by 2 factorial, or in this side I can say a0 will be every time I will get, so minus omega squared 2 factorial into a0. Now put what is j equal to 2, put j equal to 2, when a4 will be minus omega square a2 divided by j is 2. So it will be 2 plus 1 and 3 into 4. 3 into 4. And you put a2 is actually your minus of this, right? So if you substitute directly, this will be omega raised to 4 a0, sorry, omega 0. 2 factorial into 3 into 4 is simply 3 factorial and multiplied by a0. Minus and minus cancels. Omega square into omega square is omega raised to 4. A2 is replaced by this. So A0 is coming. 3 into 4 into 2 factorial is 4. No, 4 factorial, not 3 factorial. And obviously put one more term. Will give you the, this is enough actually. What will be the general term? Okay, put j equal to 4. Why? What happens when j equal to 3? J equal to 3 we have already seen. All odd powers of odd coefficients are 0. Okay, there is no point in looking for that. J equal to 4. A6 is equal to minus omega squared A4 divided by, when it is 6, it will be 5 into 6. Okay, you have put j equal to 4, 4 plus 1 into 4 plus 2. And obviously this will be, without much, minus omega raised to 6 by 6 factorial A0. So let's look for, what is j equal to 2n. Okay, instead of all even numbers will be coming. So what is the general term? A2n is equal to, there is a minus term coming in, so alternately, so when minus 1, when n is 1, A2 is minus, there is a minus sign, so that is easy. So you can just say minus 1 raised to n into omega, when this is 2n, 6, you have 6 here, 4, there is 4, so it is 2n divided by the same 2n whole factorial into A0. So you got an expression for a to n. But see, what are we looking for in the original equation? We have assumed that y of x is equal to a lambda x raised to lambda plus k. If you get an expression for a lambda, the rest is known, except for the k. Okay. So all we are looking for basically is a lambda, and then we will see what is going to happen. Okay. Now, using that, a to n is known, k is already known, k is 0 here. So what is our y of x? Y of x is originally lambda equal to 0 to infinity a lambda x raised to lambda plus k. So s raised to lambda plus k is not needed, s raised to lambda, because k is 0. So, and a lambda and every term, so it will be a1 plus a0 equal to, let me write it, a0 x raised to 0 is constant, plus there is no need to write a1 because a1 is already 0, so we will write a2 x raised to 2 plus a4 x raised to 4 plus etc. This is the solution, and this solution is equal to a0. A2 was nothing but minus omega squared. So let me, everywhere a0 is this, I can straightforward write it in as a common factor. A0 1 minus omega squared by 2 factorial into x squared, omega squared x squared by 2 factorial plus omega raised to 4 x raised to 4 by 4 factorial plus minus omega raised to 6 x raised to 6 by 6 factorial plus etc. What is this? It is cos omega x. What is cos x? 1 minus x squared by 2 factorial plus x raised to 4 by 4 factorial minus x raised to 6 by 6 factorial. Quickly, so this is the first solution, which is not surprising. Cos omega x, a0 is a constant term, cos omega x is the solution, general solution. A0 will come from the boundary conditions of the equation. Okay, so you will have to use appropriate boundary conditions to find out what a0 is. And what about the second solution? Second solution, again we have to put k equal to 1 here. So let me put another page. We will put this equation again back and we use the case 2. Case 2 is what? K equal to 1. K equal to 1 and put j equal to, again the same way, put j equal to 1, no, j equal to 0, okay, j equal to 0 will give you j equal to 0 will give you again a2 is equal to omega square minus omega square a0 divided by 2 is a k equal to 1 there, so it will, we will have one more term, right? Instead of 2 plus 1 it will be j plus j is 0, so k plus 2, k is 1, so it is 1 plus 2. So 2 into 3 is equal to again minus omega squared by this is 3 factorial a0. Similarly, going by j equal to 2, you will get, let me write it straightforward because it is not a4, it will be minus omega raised to 4 a0 divided by, instead of 2 into 3 it will be 3 into 4, 4 into 5, 4 into 5, so it will be minus omega plus sorry, omega square a2, which is plus omega raised to 4 by omega raised to 5. No, sorry, there is no 4. This is 4 itself. 4 by 5 factorial. Here the denominator madre maru. And so a similarly going by a5, a6. a6 is equal to minus omega raised to 6 a0 divided by 7 factorial. Let's do the substitution. Straightforward, y is equal to summation over lambda equal to 0 to infinity a lambda x raised to lambda plus k, and k is 1, so it is 1. So this will be a0 x raised to lambda a0 x raised to 1 plus a1 x square plus a, oh no, a1 is not there, so I can avoid straight away. A2 x raised to, it's actually 3 plus, I mean the other term is also there, a1 x squared is also there, but a1 is 0, so we are avoiding it. A4 x raised to 5 plus etc. Now substitute for this a0 x a0 as usual. Okay, wait, ഇവിടെ നമ്മൾ രണ്ടാമത്തെ സ്റ്റെപ്പിൽ എഴുതാം കാരണം a0 x plus a2 is minus omega squared by 3 factorial minus omega squared by 3 factorial a0 omega squared x cube plus omega raised to 4 a0 by 5 factorial into x raised to 5 minus etc. Then obviously if the earlier one was sin x, cos x, this will be sin x. La. So to match, actually here you see, I mean cos omega x, omega 1 omega is missing, so you just instead of taking a0 out, you take a0 divided by omega, so that this will be omega x minus omega squared x squared, no, omega cube 1 omega cube x cube by 3 factorial plus omega raised to 5 x raised to 5 by 5 factorial minus etc., which is nothing but AC sin omega x. Okay, so we found that, I mean, I said don't worry about this thing, because this you can always, constants are immaterial, constants you cannot identify using this method, and not generally constants cannot be determined from any unless you apply boundary conditions. Okay, so we find that fairly lengthy, but it is surely giving you a result here. Okay, so you get, what did we do? We first the method, let me add a page and quickly, the method is at first we use a power series for this. Second, in that obtain indicial equation by putting lambda equal to 0 and equating the lowest coefficient, okay, lowest power of x, equating the lowest power of x terms, okay, we get the indicial equation. Second, third, you make a1 equal to 0, the second coefficient is 0. For obtain the recurrence relation, convergence, okay, assume convergence or termination basically, and will lead to the recurrence relation. And in the recurrence relation you substitute the solutions of the initial equation, use these to find out the solution. Here this equation, see for example, let's look at this term. This is this, where was that? The first two equations. Okay, let me take again this out. Oh yeah, we don't know. Okay, now go to d squared y by dx squared. So nothing, this was our equation. So I can say that omega squared as the first term, or sorry, y double dash as the first term, first line, and second term as omega square. I am not doing anything complicated. Look at this term, term by term I am writing. The first term, lambda is equal to 0 to infinity. Lambda is equal to 0 to infinity. So first term is lambda equal to 0 will be k plus k minus 1. Yeah, let me take the a0 first for the sake of a0, and when lambda is 0, this is k into k minus 1, x raised to lambda is 0, so it is k minus 2, plus the second term is a1 into, so where lambda is 1, okay, lambda is 1, so k plus 1 into k plus 1 minus 1, so it will be k into k plus 1. It is k plus 1 into k, x raised to k minus 1, plus a2, when you put lambda equal to 2, this will be k plus 2 into k plus 1, x raised to k, plus we need one more term, a3 k plus 3 into k plus 2, x raised to k plus 1, all of small case, there is no capital K, plus it goes on like this, plus, okay, it goes on, and I had the second plus, okay, this is that in this equation y double dash plus omega squared y, everywhere I will multiply omega squared and y is this one, so when I put lambda equal to 0, I will have lambda equal to 0, a0 x raised to k, so I have a x raised to k term only here, so that term is plus a0 omega squared x raised to k, plus what is the when lambda equal to 1. Why did I write it here, not here? Because it is equating the powers of x raised to k here, x raised to k here. When I put a lambda equal to 0, lambda equal to 1, I have a1 omega squared, a1 omega squared x raised to k plus 1, plus etc. Now obviously there are no terms with x raised to k, so you can write that to match 0 into x raised to k minus 2 plus 0 into x raised to k minus 1. And this is what precisely we got. A0 into k minus 1 is equal to 0, from which was our indicial equation. A1 into k plus 1 into k equal to 0 was our second indicial equation. And term by term you equate, and later, so there is no surprise that A0 is related to A2, because this coefficient is equal to this coefficient. This is our recurrence relation. Okay, so go ahead, and after some time it should stop. So you say that the convergence is guaranteed. So this is the method. There is one more trick. I mean, like you can, instead of, if the equation is having x a constant, you can generalize this y of x to include y of x as summation lambda equal to 0 to infinity a lambda sum x minus x0 raised to lambda plus k. Again, a0 not equal to 0. That's fine. So we will look into the more details. I mean, so you can expand with respect to a point other than x equal to 0, x equal to k also. Okay, that's fine. So we will stop here.